Okay, now, after viewing the video on the purpose of gluconeogenesis, let's look at the reactions plus regulation of the gluconeogenic steps. Now, there's different ways of looking at gluconeogenesis, but what I'd like to do is start at what I call the fork in the road. And the fork in the road is going to be down around the pyruvate reaction. So what we've seen before is in the fed state, pyruvate enters the mitochondria and is converted to acetyl-CoA by pyruvate dehydrogenase enzyme. The TCA then, or acetyl-CoA then enters the TCA cycle, producing NADH, which will go on to support ATP synthesis. So this is in the fed state. Now, in the fasting state, what we are going to do is we are going to change the direction of pyruvate. So the pyruvate now will move into a different direction. And this direction that it's going to move into is going to be mediated by a carboxylation reaction. And what we are going to form is a TCA intermediate. And this TCA intermediate is oxaloacetate. So this is a carboxylation reaction. So CO2 will be added into this reaction, and the enzyme that does this is called pyruvate carboxylase. Now the question becomes, what determines which enzyme is going to be used? Is it going to be pyruvate dehydrogenase or pyruvate carboxylase? This determination is dependent on the concentration of acetyl-CoA. Because recall, the pyruvate dehydrogenase enzyme is negatively regulated by acetyl-CoA concentrations. So this is a feedback inhibition of acetyl-CoA to inhibit pyruvate dehydrogenase and inhibit the conversion of pyruvate to acetyl-CoA. So if we have elevated levels of acetyl-CoA, elevated concentrations, we can inhibit pyruvate dehydrogenase and we can promote pyruvate carboxylase, because the same high concentration of acetyl-CoA now becomes a positive regulator of pyruvate carboxylase. Once that happens, the pyruvate now will be converted into oxaloacetate through the carboxylation reaction. Now the question becomes, where does the acetyl-CoA come from? Well, in the fed state, we know that it's coming from pyruvate, but in the fed, that's the fed state. We're talking fasting for gluconeogenesis. Well, recall that fasting means glucagon signaling. Glucagon signaling will cause fatty acid hydrolysis and release from adipocytes. The fatty acid then enters the bloodstream, the liver takes up fatty acids through the fatty acid transport protein on the plasma membrane, and then will undergo beta oxidation to convert the fatty acids into acetyl-CoA. This happens again in the fasting state due to glucagon signaling. So the acetyl-CoA levels are increased because of the beta oxidation. These levels now inhibit the pyruvate dehydrogenase and activate pyruvate carboxylase. So the fork in the road, the shift of pyruvate conversion, is determined by acetyl-CoA levels, which are determined by the fasting signal glucagon. Now, once we have our oxaloacetate, in the mitochondria that is formed from the pyruvate carboxylase enzyme, we are going to convert this to malate. And this is going to be done by the malate dehydrogenase enzyme. Now recall, the normal TCA direction is from malate to oxaloacetate. But also recall that this enzyme, malate dehydrogenase, has a delta G of positive 7.1 in the direction of malate to oxaloacetate. So, how do we go from oxaloacetate to malate? Well, first of all, the concentration of oxaloacetate is rapidly increasing because of the pyruvate carboxylase reaction to convert pyruvate to oxaloacetate. So this is increasing our substrate of this reaction. The malate is going to be disappearing because this malate is going to be used for gluconeogenesis purposes. Also recall that the NADH concentration in the mitochondria is extremely high because we have acetyl-CoA at very high levels, which is coming from beta oxidation of fatty acids. Remember, we are in a fasting state in the liver. So we have lots of fatty acid beta oxidation going on, generating a lot of acetyl-CoA. The acetyl-CoA, of course, is used at our fork in the road to inhibit pyruvate dehydrogenase and activate pyruvate carboxylase, but it is also feeding the TCA cycle. Whenever the TCA cycle can function in this state, in the high energy state, keeping the NADH levels very, very high. High levels of NADH, recall, inhibit the forward direction of malate to oxaloacetate because we have a depletion of NAD. Because we have high concentrations of NADH, we have low concentrations of NAD, so thus the redox reaction from malate to oxaloacetate is going to be inhibited because we do not have the cofactor NAD to receive these electrons. So the upshot of this is that all of these purposes, all of these reasons are going to promote the direction of malate dehydrogenase into reducing oxaloacetate into malate. And again, because we have high concentrations of NADH, and so we can promote this direction. Now, I also said malate was disappearing. Where's malate going? Well, malate is now entering the cytoplasm. Now Now what happens to malate in the cytoplasm? Okay, let's go to the next slide. So malate in the cytoplasm is increasing its concentration because of the conversion of oxaloacetate, the reduction of oxaloacetate to malate. Malate enters the cytoplasm through the malate shuttle, and then once in the cytoplasm, now is converted back to oxaloacetate. And this is done by the malate dehydrogenase enzyme, which is the same enzyme that we saw used in the fatty acid synthesis pathway. But in this case, what we're doing is we're taking reducing power from the mitochondria in the form of malate and we're going to oxidize malate and reduce NAD plus into NADH, generating oxaloacetate. Now the oxaloacetate will form the next product for gluconeogenesis. NADH will now go to fuel glyceraldehyde 3-phosphate dehydrogenase, because we are going backwards now in glycolysis. We'll get to that in a second. So the oxaloacetate now that's in the cytoplasm will be entering the reverse direction of glycolysis. So oxaloacetate, the first step we are going to do here is convert this into phosphoenol pyruvate, also known as PEEP. This reaction is going to be a decarboxylation reaction, and we are also going to use the energy here of GTP. Recall, because the structure of phosphoenol pyruvate is generating a high energy bond between the middle carbon and the phosphate residue. So here's phosphoenol pyruvate, and we are generating a high energy bond right there. So in order to construct this, we need to use the energy of GTP. Now once we form phosphoenol pyruvate, we can go backwards in gluconeogenesis and take ourselves back to 3-phosphoglycerate. Remember, all of these reactions are reversible in glycolysis, and it all depends on substrate-product relationship to drive that delta G into the negative values, and we are increasing our product in this case because we are feeding the gluconeogenic pathway, so substrates are coming down the path. So we have now glycerate, and from 3-phosphoglycerate we are going to continue glycolysis in the reverse direction to form 1,3-bisphosphoglycerate or 1,3-phosphoglycerate. Then the next reaction is going to be the dehydrogenase enzyme going backwards. And here we are going to form glyceraldehyde 3-phosphate. And this is done by the glyceraldehyde 3-phosphate dehydrogenase enzyme. Now, of course, we're going backwards in this reaction, so we're not generating NADH, but in fact, we are using NADH, converting that into NAD. So we're oxidizing NADH in order to generate glyceraldehyde 3-phosphate. This NADH is being supplied by the oxidation of malate as it comes out of the mitochondria, converted to oxaloacetate, which then goes into phosphoenolpyruvate. Now let's go back one step to phosphoenolpyruvate. So phosphoenolpyruvate, you know the normal reaction here is going to be converted into pyruvate in glycolysis by the enzyme pyruvate kinase. And in doing so, this is one of our ATP generating steps. Now, if we are generating in gluconeogenesis phosphoenolpyruvate from oxaloacetate, then we are supplying potentially pyruvate kinase with substrate in order to go back into pyruvate. Then from pyruvate, we would technically have to convert this into oxaloacetate, malate, back out into the cytoplasm. You're seeing what's happening here, and then into oxaloacetate. But this is inhibited. This is one of those feudal loops that I mentioned in class. And the feudal loop is going to be a net zero gain on the cycle. So we need to find a way to inhibit this. And the way we inhibit this is, remember, we are in a fasting state. So glucagon will signal in the liver down its signal transduction pathway, cyclic AMP, all the way down to protein kinase A. Protein kinase A will phosphorylate pyruvate kinase and inhibit this reaction of phosphoenolpyruvate to pyruvate. And therefore, all the phosphoenolpyruvate that we generate can now be used for gluconeogenesis. So the feudal loop is inhibited in this case. I think I forgot to mention the enzyme that converts this. This is phosphoenolpyruvate carboxy kinase that converts oxaloacetate into phosphoenolpyruvate in the cytoplasm to enter these carbon sources into the gluconeogenic cycle. Okay, now we're back up to glyceraldehyde, 3-phosphate. Recall that we can convert this into DHAP because we are increasing our concentration of glyceraldehyde 3-phosphate because we're going reverse in glycolysis due to gluconeogenesis. So this is going to drive the triose isomerase enzyme to form DHAP because we will have, again, a negative delta G because of the high concentration of substrate, lower concentration of product. Then these two we are going to reverse. The reactions, aldolase, to form fructose 1,6-bisphosphate, and yes, now we have another problem. Because this direction by PFK1 is not going to happen. Remember, because PFK1 is a kinase that is going to hydrolyze ATP, this is one of our ATP utilization steps, in order to generate fructose 1,6-bisphosphate, but the reverse reaction is not reversible. So what we're going to need here is another enzyme to bypass this inhibited irreversible reaction. And the enzyme that will reverse this reaction is phosphofructo phosphatase. The other name that you will see in textbooks is related to the product of this reaction. So it's 1,6-bisphosphate, bisphosphatase. Fructose 1,6-bisphosphatase, because it's going to remove the phosphate on the number 1 carbon of fructose in order to generate fructose 6-phosphate. Now, again, we have the potential, because now we have a substrate for PFK1, so we have a potential of PFK1 reversing this reaction. This would create another futile reaction, a futile loop. So now we have to regulate PFK1 in this instance in order to prevent this futile loop. I'm going to break this video up and we'll start a new one, so this is a little bit more digestible. And we'll start out with the regulation of PFK1 in the fasting state in the liver.